So what is that? Bose-Einstein condensation. Okay, in that Bose-Einstein condensation, all of our discussion was on this n expression. Am I right? What is that? F of E, rho of E d. Am I right? The what you call comment was, what is that? This rho of E d is not counting zero energy. That's why this expression is not so complete. Then we started writing n total number is equal to number of particle in the zero energy state plus number of particle in the excited state, like that. Okay, and the whole theory. Okay, you just work it out briefly. Fine. I mean, until now there are no question like on the process actually, but one very frequent question. Okay, fine. Bose-Einstein condensation. Okay, so at some temperature mu will be zero. Right? Mu was function of T, negative and large. Okay, when you decrease the T, mu will become zero. When mu becomes zero, this will become very finite value or something. Okay, you just go through the theory. Okay, once. Okay, now that Bose-Einstein condensation can happen. Okay, fine, only when this n, whatever the expression we write. Okay, what is this one? Rho of E d divided by e power beta e minus 1. Like mu should not be there. I mean, the discussion is when mu becomes zero. Am I right? Fine. Mu should not be there. Okay. Usually in boson, I mean helium gas and E minus mu was there. Am I right? When mu equal to zero, this number expression. Okay, this can count only particle in the excited state. Those were the idea. Okay, just recall. Fine. It won't care about number of particle in the ground state actually. Okay. Fine. Or if you work out this one, this is highly depending on T actually. That means if you decrease the temperature, how total number of particles must be fixed, am I right? Got my point. I mean, that kind of question was coming actually. Okay, read that one. Okay, now this must be, okay, this integral 0 to infinity, this must be finite. Okay, in order to have Bose-Einstein condensation. This became finite, and depending on temperature, that was the problem. Like it was total number of particles. Am I right? It should be fixed actually. It should be only some material dependent or something. Am I right? It should not be time. Okay. If suppose if it depends on temperature, if you keep on decreasing the temperature, if it decreases, where those particles are going? That means this expression was not taking care about particles in the zero energy state. Okay, that was the idea. Okay, now this must be finite in order to have Bose-Einstein condensation. Okay, fine. Now what is this one again? If I work out, so constant into e power d by s minus 1 dE. Okay, this is again one Riemann-Zeta integral discussion. Now when this integral is finite, so that is, okay, when, okay, d by s is greater than 1. Your Bose-Einstein condensation can occur only when d by s is greater than 1. Okay, this was given in one old CSIR net exam. I'm giving almost as it is. Okay, because earlier I used some that Wolfram alpha calculator to evaluate whether it is finite or not. Okay, but now it is not available. Fine, d by s must be greater than 1 in order to have Bose-Einstein condensation. Okay, that is question 2 to 3 times in 5 marks part actually. Okay, so that's a question 2 to 3 times. Okay, you check this out. Okay, I have 1 or 2 question here. 3 question in CSIR net. The dispersion relation of a gas E of k, A k power s. Okay, fine. In d dimension, can you see here? D dimension. Okay, k power s. Okay, fine. Bose-Einstein condensation can occur for all values. D by what I said? D by s is. Can you check once? That right? D must be greater than s. Fine. Is that okay? That's one question. So I mean, then okay, that's quite, again, once it became frequent, they also now again we will remember that one. Am I right? This was the one. Okay, this was the question. I mean, when I look back the theory, it seems what you call feasible. Am I right? I mean, finite value of this one was the trouble. Am I right? At finite temperature. I mean, low, not at 0 Kelvin. At 0 Kelvin, all goes to ground state. That's the idea. Okay. So greater than 0 Kelvin, but at low temperature, this was finite depending on T. That was the trouble. Am I right? That should happen in order to have Bose-Einstein condensation. Fine. I mean, greater than 0 Kelvin at low temperature. Okay, fine. So this should be finite. Okay, fine. That's the basic idea. Okay, so that is this question only, I think. Okay, so whatever I have referred. Okay, what is that? For Bose-Einstein condensation to occur, okay, number of particle in the excited state. Okay, when I mean, should remain finite even for mu equal to 0. This should remain finite when mu equal to 0. Fine. D by S minus 1 only. Check that out. So from this question only I got this idea. Okay, D by S is greater than 1. But at that time, this was very old question. Okay, at that time I used that Wolfram alpha calculator. Okay, to conclude that one. D by S is greater than 1. Fine. So now look at here. Okay, two questions are there. Quite. I mean, you may remember and proceed. Okay, but how do you solve this question? The system of non-relativistic and non-interacting bosons of mass m in 2 dimensions. Non-relativistic means S equal to 2. Dimension is 2. I answered actually. The Bose-Einstein condensation temperature Tc is. He's asking temperature. Huh? How do you do? What is D by S? 1, not greater than 1. That means it won't happen. It can happen at 0 Kelvin. 0 Kelvin, all particles should go to ground state only. 0 is the answer. And it's a 5 marks question. You got on. It won't happen at any finite temperature. It can happen at 0 Kelvin, it will happen. I mean, the idea is, okay, greater than 0 Kelvin, at low temperature, suddenly all particles started accumulating the ground state. That was the condensation stuff, isn't it? That won't happen for this one. There is no temperature other than 0 Kelvin. Okay, it is 0 Kelvin. Check this out. You got me? So E is equal to h bar square k square by 2m. That's why S equal to 2. Okay, dimension equal to 2. D by S equal to 1. BEC will not happen. Okay, fine. And if you think, okay, if you think that it is happening, it can happen at 0 Kelvin. Like all particle goes to ground state. Fine. BEC cannot occur. Okay. So at 0 Kelvin, it can, you can say. But that's not any surprising fact, am I right? At 0 Kelvin, that's not any and bosonic system, any particle can be placed in single particle level. 0 Kelvin means you are trying to decrease the system energy as low as possible. So that will happen. Okay, that's not any surprising fact. Okay, fine. Grab this idea. So that's one part. Okay, and I have one more question here.
It is not on how we compare to T.
No, that actually you need to work out one of those expression. What is that?
So E bar any relation to T? With T?
No, I mean what I'm saying is, okay. How did we find TC? Can you recall? We use the same expression actually. Trick was the same expression. N is equal to, okay. What we did? How did we find TC? Huh? Equal to 0, and we use the same expression actually, same N expression, but TC actually, okay, 0 to infinity. What is this one? Rho of A D, okay, e power, what is this one? E by KB TC minus 1. We again, by substituting, we try to take this Tc outside. It's quite, I use some limit and all to convert. This is right, am I right? I put T equal to Tc and solve Tc, I found Tc, okay? Tc proportional to N by V. What was the usual one in that one? 2 by 3. Condensation temperature, I mean, in the usual one, this is different. He made 2 dimension, okay? Fine. So check this out. That should be worked out, okay? I think, no, what I'm saying is, while working out again, you put E by kBTC equal to some constant and try to take the temperature term outside. The rest of the integral is not finite. For this d by s, which is equal to 1, the rest of the integral is not finite. I used to assume that that is finite, am I right? In d by theory and all. Now it is not finite, okay? When it is greater than 1, then only it is finite. That is the idea. Grab this one, okay? So, I mean, look at here. They did design the question like, if you should quickly observe that one. It won't happen at any finite temperature, okay? Fine. Because if you, the expression that we are using to find Tc, that is blowing up to infinity, okay? Check that out. Fine. I mean, this integral is not finite, okay? That is the idea, okay? Fine. I mean, since I'm not proceeding further, because, so that is again one more Riemann-Zeta integral discussion actually. This one, okay?